Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll implement artificial neural networks. We begin by importing NumPy and setting up a random number generator (RNG) with seed value of 42. The random number generator will be used throughout the Colab to ensure reproducibility of experiments. We shall start writing the network class. The two methods that are indispensable for ML class are fit and predict. Fitting a neural network model requires us to compute two passes on the data, namely forward and backward pass. We need to start at some place by initializing the network and various hyperparameters, and this requires an init method. In most of these methods, we would have to take help of certain helper functions like activations and losses. This is the process, but we'll work through it in reverse order so that each step of the process does not have any forward reference. So we'll start with helpers, then implement init, then forward, then backward, then fit, and then predict. The skeleton of the class is given in this particular code block that I have highlighted. For the ease of exposition, we are going to discuss the methods one at a time and then plug them into the class right at the end. So in this class, we have implemented init, forward, backward, fit, and predict methods. Init method takes activation choice, output choice, and loss choice and layers as parameters. Forward function takes feature matrix as a parameter, whereas backward takes the actual label and predicted labels as parameters. The fit function takes feature matrix and the output label as parameter along with learning rate, number of epochs, and batch size. And predict takes feature matrix as the parameter. Let's first implement the helper functions. So for hidden layers, we are going to use two activations, sigmoid and ReLU. Both these activations will be applied element-wise, and the input to these functions can be scalar, vectors, or matrix. You know sigmoid is calculated as 1 by 1 plus e raised to minus z, whereas ReLU is simple piecewise linear function that returns the same value whenever the value is positive and it is 0 for negative values. So we'll also need derivatives of this function while calculating the backward pass, and deriving the mathematical expressions for them is left as an exercise to the learners. So implement sigmoid by taking z as an input, and this is simply 1 by 1 plus np dot exponential of minus z, and then gradient of sigmoid is calculated as sigmoid of z into 1 minus sigmoid of z. This is the gradient of the sigmoid function. ReLU of z is implemented with np.where function. Wherever z is greater than or equal to 0, we return z, else we return 0. The gradient of ReLU is implemented again with np.where function. Whenever z is greater than or equal to 0, the gradient of ReLU is 1, otherwise it is 0. Finally, we define a dictionary of activation functions and gradients, and we will be using this dictionary while initializing the network. The hidden activation dictionary has two entries, sigmoid and ReLU, and gradient of hidden activation also has two entries, one for sigmoid and another one for ReLU. And the values over here are basically the functions that are defined in this code block. We'll look at two activation functions in the output layer, mainly identity for regression and softmax for classification. So identity function returns the same value that is passed to it, whereas softmax function takes a matrix of size n by k, where k is the number of classes, and since we need a probability distribution for each data point, the softmax will be computed row-wise. So you already know the expression for softmax function. To avoid overflow, we'll subtract the row-wise maximum from each row while computing the softmax, and this is an important thing to remember and practice. We implement identity and softmax in this code block. In softmax, we calculate row-wise softmax. So here, in order to prevent overflow, we subtract max row-wise and then we compute row-wise softmax. And we assert that each row is a probability distribution by making sure that some row-wise sum is indeed 1. There are two types of losses that we'll be using: least square error for regression and categorical cross entropy for classification. The least square is computed as half of the transpose of the difference between the predicted value and actual value into the difference between predicted value minus the actual value. And here y hat is the output of the network and corresponds to predicted label, and y is a vector of target label of n data points. While calculating cross entropy or categorical cross entropy loss, we are using y, the matrix of target label for n data points, and y hat is the output of the network and corresponds to predicted probabilities. And it is implemented by performing a matrix vector multiplication like -1. This is a vector of size n. We take transpose of this vector and multiply this with element-wise product between the actual values and the log of the predicted probabilities, and then we multiply this with vector of 1 of size k. So here we implement least square and categorical cross entropy loss. Least square is implemented as 0.5 into np.sum. We take the difference between the predicted value and actual value and multiply that with the same quantity, which is the difference between predicted value and actual value. Whereas categorical cross entropy loss is obtained by performing -1 into sum of y into log of the predicted probabilities. So in our implementation, we assume that arguments to the loss functions are always matrices of size n by k. In case of regression, k is equal to 1. Then comes initialization. There are two parts to it. One is network architecture initialization and weight initialization. So as part of network architecture, there are two components. One is number of layers and number of neurons per layer. We'll use L to index the layer. The network has capital L layers in all. L equal to 0 represent input layer. Any value of L between 1 and L minus 1 is will represent hidden layer, and L equal to capital L is basically the output layer. We shall represent the number of layers and the neurons using list layers. The variable L will never make an explicit appearance anywhere. Instead, we'll use range length of layers to iterate through the layers. So for input layer, the input layer is represented as layer 0, hidden layer is represented, the first hidden layer is represented as layers 1, and the nth hidden layer is represented as layers L, and the output layer is represented as layers of -1 or layers of capital L. So one useful task is to compute the total number of parameters in the network, and this can be used to make sure that network has been set up properly. So here we have implemented a count params function that takes layers as argument. So number of parameters we initialize to 0, and then we iterate through the layers, and for each of the layers we compute the number of weights and number of biases and add number of weights and biases to the number of parameters, and finally we return the total number of parameters across all the layers in this network. We test this count parameters by setting up a network with 64 neurons in the input layer, 5 neurons in the hidden layer, and 10 neurons in the output layer. And we make sure that this is indeed equal to 64 into 5 plus 5, and we add 5 into 10 plus 10 to it. So you can see that for this particular layer, the total inputs will be 64. So each neuron will have 64 inputs. That's why we have 64 into 5 weights. And since there are 5 neurons, there will be 5 biases, corresponding biases, right? And as far as the output layer is concerned, it will have, each neuron will have 5 inputs from the previous layer. That's why this is 5 into 10, these many weights. And since there are 10 neurons, there will be 10 biases. And that's why the total number of parameters should be the sum of the parameters in this layer and parameters in the final layer. Let's perform parameter initialization. The weight matrix at layer L has size of layer L-1 into layers of L. The bias at layer L is a vector of size layers of L. We'll store all these weights in list W of the same size as layers. WL would correspond to WL. Since there are L weight metrics, W0 would be set to none. Recall that the size of list is L plus 1. A similar list would be required for B. To make gradient descent update simpler, it would be useful to have a master vector theta that references all the parameters in the network. We'll do the same thing for gradient of theta. So whenever theta is updated, the weights will also be updated and vice versa. One way to do this is to start with master vector and then reshape chunks of it into dimensions of a weight matrix. Reshaping an array usually returns a view of an array and not a copy, and this is very efficient. To understand this function better, you can read NumPy documentation in copies and views. So this is the init param function that we have implemented that takes layers as an argument, and we first calculate the total number of parameters in this network. Then we define a list for weights, then for biases, for gradient of loss with respect to weights and gradient of loss with respect to biases. We sample from standard normal distribution to initialize the parameters. So the gradients is initialized with 0 that you can see over here. Now start comma end specify the portion of the theta that corresponds to parameters WL and BL. So initially we set start and end to 0, and for every layer we get the corresponding weights, the gradient of that weight, as well as biases and gradient of loss with respect to biases. And then we return theta, g theta, w, b, gw and gb. We can test this initialization of parameter for layers. The first layer has 64 neurons, second layer has 32 neurons, and third layer has 10 neurons. And we initialize the parameters and we check if the weights are views of master vector by adding bunch of assert statements over here. Now we are ready to initialize the network. So we initialize the network with activation choice, number of layers or the layers, output choice and loss function. So we set self.layers to layers, then self.theta, self.gtheta, self.w, self.b, self.gw and self.gb. We initialize all these parameters of the class by calling init params with layers as an argument. Then we set the activation functions and their gradients. So we set hidden activations as well as the output activations. And finally, we set the loss function. Let's implement the forward pass, and in forward pass you know that there are two operations. One is pre-activation or linear combination followed by nonlinear activation. So implement the forward function by taking the feature matrix as an input and performing two operations. One is a linear combination or pre-activation followed by the nonlinear activation that is obtained with ghead. And ghead, if you remember, is where we had stored the activation functions to be applied for every layer. Finally, the output activation is computed by using gout, and gout has the activation for the output layer, and we obtain the output activation, and that is returned as the return value of the forward function. We have studied backward pass algorithm in detail in our slides, and we repeat it for your convenience over here. We first initialize the gradients of the pre-activations at layer L, and those are initialized to the difference between the predicted value and actual value. So these are the gradients of pre-activation at the final layer L. It is fortunate that this is true for regression and classification. So for both regression and classification, we have exactly the same gradient of pre-activation at the final layer. The other gradients can then be iteratively updated using the following equations, where the gradient of loss with respect to W is calculated as activation of layer L minus 1 transpose into the gradient of loss with respect to Z of the layer L. Then BLG in the similar manner is calculated as ZLG transpose into the vector of 1 of size n. Then AL minus 1G is calculated as Z1G into WL transpose, and ZL minus 1G is calculated as AL minus 1G element-wise product with G dash of ZL minus 1. It is important point to note the use of self.jw1, and then there are two colons while updating the gradients of the weight. So we are using this particular expression and not simply this part of the equation. And this expression does in-place update, thus maintaining a link with the master parameters that are maintained or that are initialized in the init function, which is self.theta. So implement the backward pass in this function over here that takes the actual values and the predicted values as input, and then we go on updating the gradients of loss function with respect to weights and biases as well as activation and pre-activation in every layer. Then we implement a fit function. Once that we have all the gradients to fit a model using gradient descent, we'll use mini batch gradient descent. The batch size, learning rate, and number of epochs will be hyperparameters of this particular function. We maintain a list of losses in every epoch, and in every epoch we first compute the loss. For computing the loss, we calculate the forward pass, we perform the forward pass and obtain the predicted values, and using predicted values we call the loss function and append the loss value to the loss list, and then we use rng.shuffle to maintain reproducibility, and finally then we have number of batches and we perform mini batch gradient descent for those number of batches. So in every batch of computation we get predictions for the batch, we compute the gradients for the batch, and then we update the gradients of all parameters. Finally, we can use a trained model to predict the label. So we define a predict function here that takes feature matrix as an input, and we perform the forward pass by calling the forward function with feature matrix as an argument. We obtain the predictions. For regression, what we do is we return the prediction itself, and for classification we perform the argmax on the prediction row wise and return the class labels. Finally, we can plug in all the methods into our class. We had already defined our class and defined the methods, and now what we do is for every method we basically plug in the methods that we had implemented over here. Now we'll demonstrate the utility of our implementation on digit classification, and this digit dataset is what we studied in the previous week. So we import a digit dataset from sklearn, and digit dataset has 1797 samples, and each image is of size 8 by 8. We perform one-hot encoding of the labels, and then we use train test split from model selection, and we split the data into training and test set. We perform one-hot encoding of the training and test labels. So now we have training data of shape 1078 by 64 and test data of shape 719 by 64. The labels are of shape 1078 by 10 and 719 by 10 for train and test set respectively. So you can see that the labels are in one-hot encoding format. We initialize the network where we have I size 32 and O size. So I size is the size of the input, which is 64 in this case. Then we are using one hidden layer with 32 neurons, and in the output layer we are going to use 10 neurons because that is what we want. We want prediction across 10 classes, or we want a probability distribution over these 10 classes. We instantiate a network object with activation choice sigmoid, output choice as softmax, and loss choice as CCE, or categorical cross entropy loss. We fit the network for 50 epochs with learning rate of 0.01 and batch size of 10. And then we plot the losses on the learning curve. So we have epoch on the x-axis and categorical cross entropy loss on y-axis. You can see that as the number of epochs increase, the loss is continuously decreasing, which is a good sign of training going well. And at the end of the training, we obtain accuracy of 96.24 on the test set. And in our network, there were 2410 parameters. So in this collab, we implemented artificial neural network from scratch. Hope you got a good idea about how to implement a neural network, the forward, backward operations, as well as training of neural network and obtaining predictions from the neural network. We also demonstrated the use of this neural network in predicting digits in the digit dataset from sklearn.